right, let's look at another example of setting up a triple integral. So this time we're going to try and find the volume of the solid that's above this surface, z equals square root x squared plus y squared, and below this surface, x squared plus y squared plus z squared equals z. Okay, so as usual, the first thing to do is get to be friendly with your surface. So let's see. So you can use whatever tools you want to figure out what's going on in a situation like this. So if I looked at this one, the first thing that jumps out at me is I see z equals r. And I know what z equals r looks like. If I sketch it, it's going to be the one that looks like a right cone with slope of like pi over 4. This guy. Okay, and what about this other one here? Well, this is, I can complete the square, and I x squared plus y squared plus z minus 1/2 quantity squared equals 1/4. So this is one of those spheres tangent to the origin. It's moved in the vertical direction. So it's going to actually be just like sitting on top of the origin. So it'll be like this, and its center will be here on the axis at 1/2. So that point there, that's 0, 0, 1/2 is the center of the sphere. Okay, so now it says find the volume above the cone and below the sphere. So the region that we're looking at setting up is going to be, let's see. So there's the top half, and then there's the, well, more like maybe that. Okay. And then here's the coordinate axes, something like that. Actually that's too long. It's bothering me. There we go. Okay. So something like this. All right. And then so what I guess the top right here, this is the point 0, 0, 1 for whatever that's worth. All right. So let's see. So how could we set this up? So if we were to do this in Cartesian, the volume would be, let's see. So if we did the dz integral first, then we would be looking at vertical lines that go like this. So they start down here at the bottom of the cone, and then they exit up here on the top spherical surface. So we would be going from, so the cone is z equals root x squared plus y squared, and then the sphere is z equals, and then I'd have to solve this equation for z, and it ends up being like, let's see, 1/4 minus x squared minus y squared inside the root, and then add on the 1/2 after that. So that would be 1/2 plus 1/4 minus x squared minus y squared. There we go. All right, and okay, so that would leave us with the disk of radius 1/2 to set up on the ground. So that's going to be from minus square root 1/4 minus x squared to positive 1/4 minus x squared. And then we have the integral from minus 1/2 to 1/2 for the rest of that disk. And we would have our integrand, which would just be 1, and our dv, which would be dz, dy, dx. All right, okay. So not looking overly pretty. We could also try setting it up in cylindrical. So for cylindrical, the outer part changes from 0 to 2 pi, and radius from 0 to 1/2, and then the next part becomes r to 1/2 plus square root 1/4 minus r squared, which doesn't really necessarily look a whole lot better. Now we have our Jacobian of r, as our integrand, times 1, I guess. But you can see, like, when you do the first step of this integration, what's going to happen? Well, the first thing that we do is this dz integration right here. So I can just pretend that my r is actually outside the integral because it's got no z's in it. And so what am I going to get on the inside there? I'm going to have z evaluated from top to bottom, so 1/2 minus 1/4 minus r squared minus r. And then this whole thing here is going to be multiplied by the r that's sitting outside of that integral. And I'm going to have to do this with respect to dr. And the theta is no problem. That'll just turn into a 2 pi in a puff of smoke. This one I can do, right? I mean, so like when you multiply this one out, you can do it with a u substitution. You've got your r squared, and that'll give you your u. But anyway, could be done that way. Let's see. But right now, the thing that sort of jumped out at me back at the beginning when I looked at this is that up here on the top we have a sphere, and down here on the bottom we have a cone, and this cone is actually phi equals pi over 4, and so that's a coordinate surface. The sphere itself is not a sphere of the form rho equals constant, but let's see, if I go back to the equation defining it over here, that's going to be on the left side I have a rho squared, and on the right side I have rho cosine phi. So this is actually rho equals cosine phi, which is a pretty simple formula for rho. So when I go to set it up in terms of spherical, now what I'm thinking of, here, let me just get rid of this vertical line that we had left over from before. Now I'm thinking of when I have rays coming out of the origin, zip, zap, zip, zap. Where are they first inside the object, and where are they last inside the object? So these ones all start from the origin, and the origin is included in the object. So we start at the origin down at rho equals 0. And then we look at where do we leave, and so we hit the outer surface, depending on which direction we go in, through this spherical shell. So we're going to leave at rho equals sphere. And rho equals sphere is rho equals cosine phi. And now let's see, so now which angles does this go through? Well, remember, we start at the vertical, and then we swing down over the positive x-axis as far as we go, and we see that we get to phi equals pi over 4. So that's from 0 to pi over 4. And then it's a full spin. So we go theta equals 0 to theta equals 2 pi. And once again, our Jacobian is, our integrand is 1 times the Jacobian of rho squared sine phi, and that's d rho, d phi, d theta. And so I think this one's sort of the nicest one. I guess the cylindrical one is not bad either. Sometimes it's kind of a toss-up. So for this one, we can pull out the theta bit, and you can see that that's going to be giving us just a factor of 2 pi out front. And then we have the remaining integral. See, so after we integrate the rho part, we'll get from 0, we'll be left with 0 to pi over 4. And then the integral of rho squared becomes a rho cubed. When we evaluate it, it gives us a cosine cubed. So we have cosine cubed phi sine phi d phi left as our integral, and you can readily work that one out. The whole thing simplifies to pi over 8. So there's our answer for the volume.